All right, well, welcome to Recitation 3 for this summer. Figured go over some ideas that Dom talked about and lectured in a little bit more detail, and then some examples. So Dom did discuss this. I just wanted to take a closer look at it, so if you were skeptical, this would really drill home the concept. So when we're talking about lines, it turns out there's going to be infinitely many different correct answers for any given line. And so the reason for that, intuitively, you could think of t as time, and r of t is the position of some particle at time t. And so for these line equations, our particle is moving in a straight line. And so, yeah, its trajectory, its path, whatever, it's tracing out a straight line. And so if I have the particle going in this straight line, I could go, in this direction at certain speed. I could go in the opposite direction at a faster speed. I could start at different places and things like that. I can vary my speed. I'm not going to show you an example of that, but in general, yeah, there's infinitely many ways a particle could trace out any given line. And so that gives us infinitely many ways infinitely many different equations. And so just as a concrete example, we could look in the xy plane just for fun. So for example, we could have like r of t is 2 plus t, 3 plus 2t. I could have, let's say, r of t is 3 minus t, 5 minus 2t. And then finally, I could have, let's say, r of t is 2 plus t over 100, 3 plus 2t over 100. And so the idea is that I'm going to show you that these three different equations trace out the same exact line. So, okay, let's draw our xy axes and take a look. And so, yeah, at the end of the day, think about these line equations as just giving you different x and y coordinates for various values of t. So for example, at t equals 0, I get the point 2, 3 on this line. And at t equals 1, I get the point 3, 5. Okay, and so I could plug in other values of t, whatever, but that's the idea, is that I guess this particle is tracing out that line in that direction, starting at 2, 3, and going up and to the right. Okay, and so then we could do the same thing for these others. Maybe I'll just change this drawing a little bit so it'll be easier to see. But if I do t equals 0 in this equation, I get 3, 5. And if I put t equals 1, I get the point 2, 3. And so, in fact, we all know that once you have 2 points in common, it has to be the same line. And so, for that other line, we're starting at the point 3, 5, we're going in the opposite direction. And so, these two different answers could have been, if you think back to the example Don was showing, when you have 2 points, you want to get a line, you get a displacement vector, you pick a starting point. So if you had made a different choice as far as which direction you're going, which point was the starting point, then that could affect your answer like this. And so then this last one, I don't think people will usually give on a homework question. I sort of made it a little bit more complicated. But yeah, at t equals 0, we're still at the point 2, 3, right? And then at t equals 100, notice I'll have, well, 2 plus 1 is 3, 3 plus 2 is 5. So this particle is tracing out that line at the same starting point in the same direction as equation 1, but it's going a lot slower. That it takes 1 second for the first particle to go between those 2 points. It takes 100 seconds for this third particle to go between those 2 points. And so anyway, that's, hopefully if you weren't convinced the other day, this is more proof for you that, yeah, there are infinitely many different correct equations for any given line. And so that's something you'll have to be a little bit careful about when you're looking at multiple choice questions, which that's how we test in this course over the summer. So when you're coming up with a line equation, your equation might look a little bit different, but you can always confirm it's the same line by seeing that they have 2 points in common, for example. So anyway, that's that. On the other hand, with planes, you're always going to get the same equation. It might be written in a different way, but it's still the same equation. And so some of you were probably wondering about this the other day. I think Dom alluded to it, that basically we were only concerned about the direction. But let's get our hands dirty and really see concretely that any choices you make when you're coming up with a plane equation, as long as they're correct choices, will get you to the same correct answer. So yeah, let's say I want to do the plane through these 3 points. So I guess we could do PQ, displacement vector, is going to be 4, 2, 3. And PR, for example, is going to be 3, 3, 4. And so one way we could do it is to use then the normal vector PQ cross PR, which is going to be what? 8 minus 6 is 2. No, that's not right. 8 minus 9 is negative 1. 9 minus 16 is negative 7. And then 12 minus 6 is 6. And so that I could use that. So let's just keep track. So using PQ cross PR and let's say point P, that will give us the equation minus 1 times x minus 0 minus 7 times y minus 0 plus 6 times z plus 3 equals 0. So that's one way. So another way, let's say, for example, you wanted to do PQ, or what if you did it the other way around? Let's say you did like PQ, PR cross PQ, for example. And let's say point R. So PR cross PQ is still going to be perpendicular to this plane. Because, yeah, I guess the idea is, let's pretend we look at it and it looks like PQR, like this. So I guess thinking about the right-hand rule, PQ cross PR is going to look like that, right? And then if I did PR cross PQ, we know that the anti-commutativity of the cross product, that PR cross PQ is the exact opposite vector. So that still should be perpendicular to the same plane, so it should still work. So yeah, let's see. Okay, so PR cross PQ is, of course, yeah, like we just said, the exact opposite vector. So 1, 7, minus 6. I don't have to go through all those calculations to know that. But yeah, and then let's set that up with point R. So 1 times x minus 3 plus 7 times y minus 3 minus 6 times z minus 1 equals 0. And so now you're probably like, what's going on, Joe? You said it's the same equation. Well, it is, but it's just written a little bit differently, because let's do this multiplication. So if I do everything out, this will be minus x minus 7y plus 6z. And then my constants, I'll have a plus 18 on the right-hand side. So if I move that over, that's going to be minus 18 on the other side. And then if I do the same kind of thing here, I get, well, x plus 7y minus 6z. And then what? Minus 3 minus 21 is negative 24, plus 6 is negative 18 on the left-hand side, which means that it's going to be plus 18 on the right-hand side. And then, yes, these are clearly the same equation, because the one is just the other multiplied both sides by negative 1, of course. So at the end of the day, it's the same equation. And this, I do remember seeing that Dom mentioned this, that, yeah, the length of this vector shouldn't matter. So, well, and just one other thing for fun. Yeah, so if you stretch this, for example, I could use I could say use twice PQ cross PR, which is -2 minus 14, 12, right? I just stretch the PQ cross PR by a factor of 2, make it twice as long. That should still work. And I don't know, just for fun, let's use point Q just to see that, okay, we'll get -2 times, so 420, x minus 4 minus 14 times y minus 2 plus 12 times z minus 0 equals 0. And so let's play around with that. That's -2x minus 14y plus 12z. And what? Plus 8 plus 28 is 36. So that's plus 36 on the left, which means it's minus 36 on the right. Which, oh my God, it's the same equation. Because to get from here to here, just divide both sides by 2, of course. And so, yeah, as long as you're making correct choices, you will get the same correct equation. It might look a little bit different, but standard little algebra tricks, or not even algebra, I guess it's, well, algebra, arithmetic, whatever you want to think of, it's going to be the same equation. And then additionally, you might be concerned with, oh, you know, PQ and PR, what if I based everything around, what if I do like PQ cross QR? And so I think Dom talked about this last week in recitation with regards to finding areas of triangles or parallelograms, that these different correct choices don't make a difference. Let's just rehash that for fun. It's good to see. So I claim that PQ cross QR is parallel to PQ cross PR, and so gives the same equation. Okay, so how does that work? Let's see here. Let's just draw our vectors here. So this is P, this is Q, R, PQ, PR. So you can think about the way that vector arithmetic works and see that, well, QR is, well, QP plus PR, right? Going from Q to R directly, you could stop off at P first. So yeah, QP, of course, is going to go this way. So yeah, QP plus PR is QR. Okay, so therefore, I have that PQ cross QR is PQ cross QP plus PR. Well, by the rules of the fact that cross product has a distributive property with vector addition, we see that this is PQ cross QP plus PQ cross PR. But then QP is just simply minus PQ. So this is minus PQ cross PQ plus PQ cross PR. And then what do you know? Any vector cross itself is 0. So it's through the magic of the cross product that choosing a different point that you have in common doesn't make a difference. So for example, PQ and PR, we're using P. For PQ and QR, we're using Q. I actually wasn't sure that these were going to be exactly equal. In fact, yeah, these are equal. But if you mess around with orderings or other things, you might get a minus sign, and so that's why I just said parallel. And that's enough to be confident that we get the same plane equation. Yeah, so as long as you're doing correct things, you will be getting the correct answer, and that's going to continue to hold true a lot throughout the rest of this course. I've always found that that's something that confuses people at first. Like, wait, how did you know what's so special about point P? Can I use point Q instead? Can I use point R instead? And well, if it's supposed to be on the plane, then yeah, you can. So different ways of getting the same equation. Okay, and then the next thing I want to go over is just the importance of reading carefully. Let's take a look at these two examples. So for both of them, we're asking about the equation of a plane containing some point, and then there's also this line that's somehow involved. And so in the first example, we're looking for the plane that's perpendicular to that given line. So we have this line, it's given. We have some point, 1, -2, 2. And we want the plane that's perpendicular to this line and containing this point. So the picture you want to have in mind for this is something like that. That the line is going directly through the plane that we're looking for. Whereas in question 2, it says that the plane's supposed to also contain this line. So we still have the same ingredients. We have our given line and our given point, but this time we want the plane that contains those two objects. So just by thinking about it and drawing this rough picture, you can see that these are two very different questions. And it just shows you the importance of reading all these little details. That I know before I pointed this out, you probably didn't think you would have to read this carefully, as far as just changing one little detail really changes the question. But now that you know to look out for it, make sure you do. People get fooled by this all the time. Basically, this question, the first one is easier, as we'll see in a second. And so I think a lot of times people read this, but then think it's that, and they end up doing less work, and you just end up getting in trouble. So just pay attention, draw a rough little picture like this. If you want to, make sure you're focusing on the correct thing. But yeah, so anyway, for question 1, we can just use the direction of the line as the normal vector of the plane, right? Because whatever direction v points along the line is perpendicular to the plane that we want, so we can just use the same vector as the normal vector for the plane. Okay, and so we look at the coefficients of t to see that we should use 3, -1, 2 as the normal vector. And then if you use the point that's given, 1, -2, 2, you could also use any point. Well, never mind. I think this is the quickest thing to do. Use that point that we know. That's the only one we know right now that's on the line, or that's on the plane. And yeah, set it up like 3 times x - 1 minus y + 2 plus 2 times z - 2 equals 0. So yeah, we didn't actually have to do any calculations. We just had to pick off some coefficients and get going like that. Okay, and then so for the second one, a little bit different. We could still use the direction v from the line, but now that's not going to be perpendicular to this plane that we're looking for question 2. It's going to point along the plane. So what else? Okay, what else do we know? Well, this is something that I think people forget a lot, that these line equations tell us as many points on the line as we want. That all you do is you plug in a value of t, and you can get a point that's on the line. So 1, 3, 0 is a point on the line. And so now we can get a displacement vector between these 2 points, which is going to be what? 0, -5, 2. And then take this cross product of those 2 vectors to get something perpendicular to the plane that we're looking for. So that's what we need to do. So I guess the approach is we're going to cross 2 vectors that point along the plane. And the way we get those, we can use the vector for their line, get a point on the line, and get a displacement vector to the other known point, and go from there. So what is this cross product going to be? So for me, oh, that's supposed to be a positive 2. I cannot take cross products unless I have it organized visually like this. I don't know, my brain just doesn't work like that. I'd have to show too much work, which I'm not into. You guys do whatever you need to. But anyway, what? This is -2 plus 10 is 8. This is -6. And then this is -15. And so then we could use the given point. So what? 8 times x minus 1 minus 6 times y plus 2 minus 15 times z minus 2 equals 0. And that's what we're looking for there. So again, you gotta pay attention to all these little details. At first glance, these questions look very, very similar. But when you think about it carefully, you see that they're asking about quite different things. So be careful. Okay, so we'll probably do some more examples on Friday's recitation about distances between various kinds of objects. That could be a confusing topic, so we'll focus on other questions from 12.5 on Friday. But for today, I just figured get into some of the stuff from yesterday's lecture, 12.6. And so Dom talked about cylinders and this idea of you can either think of cylinders as having the same kind of cross-section and it's just all stacked up. And you see that from when the equation is missing a variable. The other idea you can think of, and this is how the book defines a cylinder, is you start with a plane curve and then you specify a direction and you call all the lines, you make all the lines with that direction through that curve, and that is going to make your cylinder. And so those lines with that given direction, that's what we called rulings. And so this is a fun little example of a cylinder example where the rulings aren't parallel to any of the axes. It's diagonal, basically. And then in addition, it just really goes to show you the power of traces. So I wouldn't worry about something like this. We wouldn't expect you to do this without a hint. Like maybe we would give you this equation and tell you to look at some specific traces. But yeah, looking at this, when I first looked at this example, I had no idea what kind of surface this was going to end up being. And it's not quite similar to, it's not exactly like some of the other ones that we've looked at. But it turns out it's going to be a cylinder, and we'll have a pretty good understanding of what it looks like if we utilize the power of traces. So anyway, let's try some z equals k traces, just to see what we end up getting. So if z equals 0, this equation is x squared plus y squared equals 1. So we get, of course, the unit circle in the xy plane. But then, okay, what happens if, say, z is 1? Well, then that's going to be x squared plus y minus 1 squared equals 1. So it's still a circle of radius 1, but now it's centered at the point 0, 1 on the y-axis, so looks something like that. So z equals 2 is going to be x squared plus y minus 2 squared equals 1. And so again, it's a circle of radius 1, but now it's centered at 0, 2. And so at this stage, you could just kind of find the patterns that z equals k is going to be x squared plus y minus k squared equals 1. So it's a circle centered at 0, k and radius 1. And so now we can imagine stacking these traces up. So we have our xy plane, z equals 0. We have our plane, z equals 1. We have our plane, z equals 2. Let me draw our axes in each of them, just so it looks nice. So, whatever, I'll use a different color. Might as well. So the z equals 0 trace was centered at the origin. The z equals 1 trace was touching the origin. And the z equals 2 trace was something like that. And so if we stack all these up, we get sort of a diagonal tilted circular cylinder as our surface. And then the rulings point of view, remember, is that the rulings are all these lines that go through. You could think of the unit circle in the xy plane as sort of the starting curve, and then you draw all these purple lines through it. And so you could just think about one of these purple lines. For example, this point here is 0, minus 1, 0, and this is 0, 0, 1. So the rulings are parallel to the vector 0, 1, 1. That 0, 1, 1 is the displacement vector between those 2 points. And so that just goes to show you the power, the real power of traces, that we have this complicated looking equation. Like, good God, I got y minus z there. What's that going to end up doing to our surface? But yeah, if you just start plugging in different numbers for z, you start to see the pattern, and then you can understand that, yeah, your cross sections are just circles that are sort of shifting as you increase z. All right. And then I think what I wanted to do is just an example of figuring out what's going on with 9 different equations. Basically one example, or maybe it's 8. I think it's 8. Well, I can't remember. We'll see in a moment. But just sort of, here's a big list of equations. What kind of surfaces are we dealing with? And so let's just quickly then review this situation for the conic sections. Remember the curves. So I didn't put parabolas on here because I think everybody's pretty comfortable with parabolas. If you're not, go back and think about it. But when you have both x squared and y squared, then I guess there's different possibilities. That if you have plus, 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 then you end up getting an ellipse. An ellipse is just a fancy way of saying a squished or stretched circle or oval shape. And you could set either x or y to 0 to find the intercepts. So basically this a and b controls how wide it is. A determines how wide it is, b determines how tall it is. Not important for this class. I guess that's called the major and minor axes. But anyway, that's the situation with an ellipse. And then when you have opposite signed coefficients for x squared and y squared, when one of them's a minus, one of them's a plus, then you get something called a hyperbola. And so there's sort of two kinds of hyperbolas. There's a left-right kind of hyperbola that's going to look something like this. And then there's an up-down hyperbola that's going to look something like that. And which one's which, I don't think you should memorize. You just kind of look at the equation and figure out which kind of intercepts it has. So if you set, in this first one, if you set x equal to 0, if x is 0, we're looking at minus y squared over b squared equals 1. And we don't do imaginary numbers in this class, so there's no y-intercepts. Whereas if you set y equal to 0, you get x squared over a squared equals 1, which means x is plus or minus a. And so you do get x-intercepts. And then sort of the opposite situation happens here, that if I set x equal to 0 here, I do get y-intercepts of 0 plus or minus b. So this is the point 0, b. And then if I set y equal to 0, I don't get x-intercepts because minus x squared over a squared will never be a positive number. And if you're interested in hyperbolas, they kind of look like two parabolas, but not quite. They actually have these diagonal asymptotes that have slope plus or minus b over a, if you're interested, but it's not going to be too important for this class. Because first of all, we're not making you draw pictures. But even if we weren't going to be super picky about that kind of thing. But yeah, just to explain, it isn't simply two parabolas put together. Parabolas don't have any intercepts, or sorry, asymptotes. But hyperbolas have these diagonal asymptotes. Okay, and then finally, the other weird cases are going to be when I guess, for example, you have minus x squared over a squared minus y squared over b squared equals 1. Well, remember, again, we don't do complex numbers, so there's no way anything squared could be negative. So basically, minus x squared over a squared minus y squared over b squared, that's guaranteed to be less than or equal to 0. And yeah, that's not 1. So you're not going to get any solutions for that. And then similarly, if I have x squared over a squared plus y squared over b squared equals 0, the only possible way that could be true is if both x and y are 0. And so these are going to be some of the things we're looking at in our traces. So as far as our basic situations go, if we did shifts and rotations arbitrarily, the equations could look a lot more complicated, but we're going to assume that we've put these surfaces into some kind of standard form. And so the things you're going to look out for when you see an equation is, first, take a look and see if any of the variables are missing completely. And so if any variable is missing completely, that's guaranteed to give us some sort of cylinder. And it's just a matter of figuring out, what are the cross sections. It could be a parabolic cylinder, it could be an elliptic cylinder, it could be a hyperbolic cylinder. For some reason, we've never really focused on that, so I wouldn't worry about that. So for us, we'll focus on 8 different quadric surfaces. And then the next thing you're going to look out for is, well, if there's one variable that's not squared, whether that's z, y, or x, something not squared is always going to end up being some kind of paraboloid. And that's easy to remember because, in the xy plane, parabolas are something like y equals x squared or x equals y squared minus 2 or something like that. In a parabola, something squared, something isn't. And so you can think of that pattern as continuing for these paraboloids. And then I guess the other possibility is if everything is squared, then that's going to end up being an ellipsoid, one of the two types of hyperboloids, or a cone, or maybe nothing, depending on if D has the same or opposite sign as A, B, and C in this situation. And so, yeah, let's take a look at 9 equations and practice thinking about what they're going to end up giving us in terms of a surface. So let's see here. Something I noticed for this first equation. So the first equation is x squared plus z squared equals 9. Well, there's no y. Y is missing, which means that all the y equals k traces are x squared plus z squared equals 9. So that's what happens when you have a missing variable, is that nothing happens when you plug in different values for that. So like, what's y equals 1? What's y equals 2? What's y equals 3? You know, there's no y, so nothing's happening, which means that all of my, my y equals 0 trace, my y equals 1 trace, my y equals 2 trace are all the same circle, which means that when I stack all these up, I get a circular cylinder around the y-axis. So circular cylinder, radius 3 around the y-axis. So again, going back to the previous slide, when you have a completely missing variable, it's going to give you some kind of cylinder. To decide what kind of cylinder, you just look at what this cross-section is. If it's a circle, it's a circular cylinder. More generally, if it's an ellipse, we could call that an elliptic cylinder. You could, squish that circle a little bit. But if I get something else like a parabola, that would be a parabolic cylinder. And so that's what's happening in this second equation. That if you look at this second equation, z is missing. Which means that all the z equals k traces are this same parabola. So yeah, y plus x squared equals 0 means that y is minus x squared. And so if you stack up this parabola a bunch of times, you get what we call a parabolic cylinder. That all of the cross sections at different z levels are the same parabola, y equals minus x squared. So missing variable, some kind of cylinder. Okay. Then let's look at these next ones. So looking at all the rest of these, equations 5 through 9, they're all squared. Whereas 3 and 4, something isn't squared. And so when something isn't squared, we know that these are going to end up being some kind of paraboloid. That was our rule of thumb. Something not squared is some kind of paraboloid. And for the paraboloids, the distinction between elliptic versus hyperbolic. What do you call a paraboloid that likes to exaggerate all the time? A hyperbolic paraboloid. Groan, groan, groan. So to determine whether it's elliptic paraboloid or, I mean, my office mate didn't even groan at that. So anyway, elliptic versus hyperbolic. Elliptic means that the squared variables have the same sign coefficient when on the same side. Whereas hyperbolic, the squared variables have opposite sign coefficients when on the same side of the equation. Equation 3, I'm going to put the squared variables together and see that equation 3 is z equals x squared minus y squared. In equation 4, it's what? Y equals 9 minus x squared minus z squared. This is going to be a hyperbolic paraboloid. And this one's going to be an elliptic paraboloid. And so if you want to go into more detail as to what they're going to look like, for example, equation 3, the z equals k traces are hyperbolas for k not equal to 0. And it's the lines y equals plus minus x if k is equal to 0. And then the x equals k traces are, well, if x is a number, z is k squared minus y squared. Those are down parabolas as far as the yz plane is concerned. And then the y equals k traces, well, if y is a number, then z is x squared minus k squared. That's going to be up parabolas as far as the x and z axes are concerned. And so this took me years to practice how to draw this. I'm fairly proud of it right now. Let's see here. I get our saddle shape or our Pringles chip shape. Yeah, so let's see here. Yeah, I get hyperbolas as my z traces. So if I slice it like z equals 1, I get that hyperbola. If I slice it z equals minus 1, I get a hyperbola. It actually changes from left, right to up, down. That's not super important. But those green curves are my hyperbolas. My x equals k traces are z equals x squared minus, or sorry, z equals k squared minus y squared. So I get down parabolas like that. And so that's going to be these red cross sections here. I guess I should make this green one down here dotted just to keep everything consistent because we can't actually see it. And then our y traces are z equals x squared minus k squared. So When k is 0, I get that. If k is non-zero, they're going to be down there. And so then this blue cross-section is my y equals k traces. So yeah, I guess when z is positive, we get our left-right hyperbolas like that. Oh, wait, so I should be careful now. Which one is which? Where are my axes? So my y traces, okay, so y should be going into the page, x should be going along the page, and then z should be up. And so, situation here, if k is positive, k is negative, so k positive, yeah, is left-right hyperbolas. K negative is up-down as far as that perspective. And so that sort of explains what's going on here, that when z is positive, it's sort of left-right in this perspective, and then like a front-back hyperbola from that perspective down there. But anyway, that was just more in-depth to reiterate why this looks the way it does. As far as identifying it, I think knowing that something's not squared, opposite coefficients, you should know, okay, hyperbolic paraboloid. Whereas equation 4, if I do my y equals k traces, I get that I can rearrange it to x squared plus z squared equals 9 minus k, which I see is going to be a circle when k is strictly less than 9. It's going to be a point when k equals 9, because if k equals 9, then that right-hand side is 0, and the only way that x squared plus z squared could be 0 is if they're both 0. And then nothing when k is bigger than 9. Because if k is bigger than 9, 9 minus k is negative, and there's no way x squared plus z squared could be something negative. And so I guess what this ends up looking like is we have this point at y equals 9, and then the cross sections to the left of y equals 9 are all circles. And if you figure out the radius, you see that it's growing as it increases, so we get this elliptic paraboloid. Just stack up a bunch of circles. All right. So let's look at what we have left. So all same sign for the squared variables. That's going to basically correspond to an ellipsoid. That, think about an ellipsoid as just a fancy way of saying a stretched or squished or compressed sphere. And so transformations work the same way in R3 as they do in R2. So if you replace z by square root of 2 times z, you're basically going to be compressing your unit sphere. That's why I crossed this 2 out at first. That if without that 2, it's just the unit sphere. But putting that 2 in basically is going to squish your z down by a little bit. And so the ellipsoid, you know, if you figure out the intercepts, you could see without too much trouble that when y and z are both 0, x is plus or minus 1. When x and z are both 0, y is plus or minus 1. And when x and y are 0, z is plus or minus 1 over root 2. So like I said, it got squished down a little bit when I replaced z with square root of 2 times z in the equation. And so anyway, that's your ellipsoid. And then just be on the lookout. I don't think we usually try to trick you guys with things like this, but equation 9 is sort of a bogus equation because guess what? Without complex numbers, there's no way x squared plus y squared plus 2z squared could ever be negative 3. So that's nothing. And so then we're left with these three, 6, 7, and 8, not same, so all squared, again, not same sign coefficients. Those are going to be the tricky ones to do. So I think for all these others, you could pretty much memorize it. You don't really have to get your hands too dirty with the traces to understand what's going on. I did here just to reiterate why these give us what they give us. But once you practice this sum, I think equations 1 through 5 and 9 you can just basically have memorized. 6, 7, 8 is going to be the real trouble. And so these are the tricky ones. I'd say for this case, get your hands dirty with traces. So basically, yeah, I really suggest if you come across an equation that has this property, that all the variables are squared, and when you look at the coefficients of the squared variables, they're not all the same sign, you really are going to want to think about traces. And it's going to be traces with the different variable. Because if you think about it, there's only 2 choices for signs, and you have 3 of them. So if they're not all the same, there's got to be one that's different from the other 2, right? They can't all have different signs because there's only 2 possibilities, plus or minus. So there's always going to be a different variable. And if you look at these equations, it's y, because for all 3 of them, x squared and z squared have the same sign coefficient, but y is the one that's opposite. And then just watch out, I could also have done minus x squared plus y squared minus z squared equals 0, for example, and y would still be different. So again, you're just finding which one doesn't agree with the other 2, not necessarily plus or minus, because you could have 2 plus 1 minus, which means the minus is the oddball, or you could have 2 minus 1 plus, which means the plus is the odd variable out. So what we're going to do for 6, 7, and 8 is look at the y equals k traces. Okay. So 6 was x squared minus y squared plus z squared equals 1. 7 was x squared minus y squared plus z squared equals 0. And then 8 was x squared minus y squared plus z squared equals minus 1. And then I think for fun, I'll add another one after we finish these. Okay, so we're going to, for all 3 of these, look at the y equals k traces. And then I like to rearrange my equations to leave our squared variables on one side, put all the numbers on the other side. And so we're thinking of k as a number. That's why we changed variables. Like you might think that, oh, I could just left y as y. But I think by changing it to k, it's sort of in your mind allows you to think, okay, for these traces, x and z are the variables. And then I'm thinking of k as just a number. So I like to organize my equations like this so I could see what's going on. So again, if y is k for equation 7, I get that x squared plus z squared is k squared. And then for equation 8, that's going to be x squared plus z squared equals k squared minus 1. And so now we just have to figure out, okay, what happens for different values of k? And so I put the simplest situation first, that 1 plus k squared is always at least 1, right? Because k squared is never negative. It's 0 when k is 0, but it's never negative. So basically, no matter what, I get a circle of radius square root 1 plus k squared. No matter what k is, I always get a circle. And you could plug in some different values and see what ends up happening, but yeah, I get like a bigger circle when k is 0, I get a circle radius 1, and I get bigger circles the further k gets away from 0, and so I'm not missing any traces in the y equals k trace family. So I just have circles that get a little smaller and then get bigger again. And so that's the idea there. And that's our one sheet hyperboloid. Okay. And then for this one, we get something a little bit more interesting happening. That if k isn't equal to 0, this is a circle of radius square root of k squared, which is absolute value of k. And if k equals 0, that's the point 0, 0. And so I pointed out the radii here to explain why the cone has sort of straight edges. That this radius is a linear function of k in each of the k positive, k negative regions. And so our hyperboloids have curved edges, but our cone has straight edges. And it shrinks down to a single point for y equals 0, but otherwise you get a circle cross section. So circle shrinks down to a point, then gets bigger. Okay, and then last one, I saved the most complicated for last. The k squared minus 1 is the most interesting because sometimes that's positive, sometimes that's 0, sometimes it's negative. So let's think about that. If k is bigger than 1 or less than negative 1, then you get a circle of radius square root of k squared minus 1. If k is equal to plus or minus 1, then k squared minus 1 is 0 and we get a single point. And then finally, if k is too close to 0, so if k is between minus 1 and 1, then k squared minus 1 is negative and we don't get anything. So this means that we have these circular cross sections that shrink down to a point, and then there's nothing for a while, and then it comes back at k equals 1 and starts going again. And so this is our two-sheet hyperboloid. That if y is too close to 0, I don't get any trace, so there's missing traces. So compared with all our other conic sections, or all of our other quadric surfaces, these three are the most similar to each other. That they have one family of ellipse traces and two families of hyperbola traces. And which one it is depends on if this ellipse family has any gaps in it. So the one-sheet hyperboloid, there's no gap in the ellipse cross sections. They shrink, they get bigger again, but they never go away. The cone, not only does it shrink down to a single point at one value of k, but also the radius is a linear function of the y value, so that's why you get these straight edges on your cone, as opposed to the curved edge on the hyperboloids. And then finally, the two-sheet hyperboloid, you have this ellipse family that vanishes for a while and then comes back. And so you might think that the cone is easy to recognize just because of the 0, but you do want to be careful. So let's do an extra bonus one. Let's say I have x squared minus y squared plus 2y plus z squared is 0. Okay. So like I said, we could get trickier with rotations and shifts and things like that. I don't think we're going to make you worry about this. If we do, we'd give you a hint as to something to try. The only things we really shift around are spheres, I would say. So be prepared for something like this with a sphere. But for a more complicated quadric surface, what are we going to do here? Well, we're going to complete the square. So this is x squared minus y squared minus 2y plus z squared equals 0. And so what I need to do to complete this square is add 1, subtract 1 in there. So be careful when you're completing the square. However you're doing it, you're doing no actual changes to the equation. And so it's a little more complicated here now that I have this minus here. But just think about it as you're adding and subtracting the same thing, and then recognizing that, okay, this is x squared minus y minus 1 squared minus 1 plus z squared equals 0. And so if you're careful, then this is going to be x squared minus y minus 1 squared plus z squared equals minus 1, right? Because there will be a plus here, and then I move it to the other side, it becomes minus. And so it turns out this is going to be a two-sheet hyperboloid. X squared minus y squared plus z squared equals minus 1, shifted by 1 in the y direction. So if you think back to pre-calc and shifting things like that, replacing y with y minus 1, I've shifted it by 1 in the y direction. And so we already decided equation 8 that x squared minus y squared plus z squared equals minus 1 is a two-sheet hyperboloid. So it turns out that equation 10 is a two-sheet hyperboloid, but all the action sort of happens around y equals 1. So it turns out then, if you go through the calculations, that y equals 2 is going to be where it comes back, and y equals 0 is when it has something like that. So yeah, just shift our previous picture over. So I guess what that means is that our origin is there. But just because you see a 0 doesn't mean you know it's a cone. But like I said, I think we will make you complete the squares for sphere situations, but you could do it for all these other quadric sections. But yeah, that's pretty much all I had in mind for today. Like I said, we could do some more distance problems on Friday. Talk about some other things. Hopefully you guys might have some homework questions posted on Piazza. I didn't really see any today. But before we wrap up, any questions for anybody here? Well, looks like a no. So yeah, have a good day, and I will see you all on Friday in this sense. So take it easy.